In today's class, we are going to discuss about magnetostatic boundary condition. So, boundary condition is nothing but we are just going to analyze the magnetic field between two areas with the help of two different mediums and how the magnetic field is going to react. So, for this magnetostatic boundary condition, there are two cases. First one is boundary condition between two magnetostatics of two different permeability. So the condition for magnetic field at the boundary between medium 1 and medium 2, and the medium field passes from one medium to another medium. This is called magnetostatic boundary condition. In order to study the conditions of B and H at the boundary, it is resolved into two components. One is called the tangential component, the other one is called the normal component. So now this diagram represents the boundary condition between two perfect dielectric. Now you could say the medium 1 is mu1 and medium 2 is mu2, and we are considering a rectangular path which is having the sides A, B, C, D, and it is having a cylindrical surface. It is having of height del h, and it is having the differential surface del s. And similarly for the rectangular path, it is having a height del h and it is having the width is del w. So now that can be resolved into two components, the tangential component and normal component. So both the tangential component and normal component are summated by with the help of B vector and H vector. So first we are going to calculate the boundary condition for tangential component. We know that by Ampere's circuitry law, line integral H dot dl is equal to I. Here the rectangular path is split into four components. That is line integral A to B, line integral B to C, line integral C to D, and line integral D to A. So therefore, the equation becomes line integral A to B H dot dl plus line integral B to C H dot dl plus line integral C to D H dot dl plus line integral D to A H dot dl is equal to the total current enclosed. So as del H tends to 0 at the boundary, what happens is, as del H tends to 0, if you see this diagram, you'll understand when del H tends to 0, then automatically B to C and D to A becomes 0. And therefore we get only A to B and C to D, that is in the opposite direction. So that is represented here. Line integral A dot B H dot dl plus line integral C to B H dot dl is equal to I. The other two components becomes 0. To find out line integral A dot integral A to B line integral H dot dl, so that is H, taking the H outside, H into line integral A to B dl, that instead of H it is replaced by H tangential 1 component as it is parallel to that path, and line integral A to B dl can be replaced that with the help of the differential with del w. Similarly for C to D it is going to be the same, but it is in opposite. So we get H tan 2 minus H tan 2 of del w. So when you add these two things, we get line integral H dot dl is equal to line integral A to B H dot dl plus line integral C to D H dot dl, and therefore it is equal to H tan 1 del w minus H tan 2 del w is equal to 0. We are assuming the current I, and therefore we get K of del w into H tan 1 minus H tan 2 is equal to 0. So that can be written as H tan 1 minus H tan 2 is equal to K. We know the relation between the magnetic field intensity and magnetic flux density. V is equal to mu into H. So in order to find the value of B, that is the above equation becomes B tan 1 divided by mu 1 minus B tan 2 divided by mu 2 is equal to K. As a special case, if the current is 0 at the boundary, and therefore we can say H tan 1 is equal to H tan 2. Since they both are same, it is continuous and it is having that value. Instead of that H tan 1, it can be written by B tan 1 by mu 1, and H tan 2 is B tan 2 divided by mu 2. Secondly, we are going to calculate the boundary condition for the normal component. For the normal component, we know that by magnetostatic Gauss law, surface integral B dot ds is equal to 0. That is, surface integral of magnetic flux density over a differential surface is equal to 0. So here it consists of three surfaces. The cylindrical surface, it consists of three surfaces. One is top, the other one is bottom, the other one is lateral. And therefore the above equation can be written as surface integral top B dot ds, the surface integral lateral B dot ds, the surface integral bottom B dot ds is equal to 0. At the boundary, what happens? The value of del H will tend to 0, and therefore we are having only the top and bottom surface and not the lateral surface. So first we are going to calculate the value of top B dot ds. Since this top is parallel to the normal component, it can be replaced by Bn1 surface integral top ds, and that can be written as Bn1 into del S. Similarly for bottom, it is the same, but it is in the opposite direction, and therefore it is minus Bn1 del S. When you add these two things, Bn1 del S minus Bn2 del S is equal to 0. That is Bn1 minus Bn2 is equal to 0, and from which you can say Bn1 is equal to Bn2. Now to find the value of H, we know that mu1 Hn1 is equal to mu2 into Hn2. Tangential component of magnetostatic of H vector and magnetostatics between the two differential permeability at the boundary is discontinuous, whereas the tangential component between two permeability at the boundary is said to be discontinuous, and therefore H tan is not equal to H tan 2. The normal component between two different quantities at the boundary is continuous. That is the only difference between these two things. This magnetostatic boundary condition, it plays a very important role as far as this two things are concerned, as discussed earlier. So first thing is we are just considering for the magnetostatic between two different dielectric. So similarly in electrostatics also we are having electrostatic boundary condition, which we discussed earlier. And there also between a conductor and free space is one case. The other cases it is between two perfect dielectric. Here therefore we are concluding here the tangential component is said to be discontinuous, while the normal component is said to be continuous. This is whereas in electrostatic the tangential component is said to be continuous and the normal component is said to be discontinuous. So that is the difference between electrostatic boundary condition and magnetostatic boundary condition. So the magnetostatic boundary conditions plays a vital role as far as these things are concerned. Now you could see from this the normal component between the two different permeability at the boundary is said to be discontinuous. It is said to be continuous. That is Bn1 is equal to Bn2, from which you can say Hn1 is also equal to Hn2. Whereas for the H tan 1 tangential component, it is not equal, and therefore it is said to be discontinuous. So these are the main things as far as this electrostatic and magnetostatic boundary conditions are concerned. That is about magnetostatic and boundary conditions. Thank you.